So we're recording. Why don't you start, Naif?
All right, yeah, sure. So hey, um, so today's tutorial is going to be on Milestone 4 and parallel programming. So let's just, okay, cool. Okay, so a lot of this Professor Betts went over in lecture, but just for a quick review, Milestone 4 goes into the traveling courier problem, which is a slight modification on the traveling salesman problem, where given depots, pickups, drop-offs, and truck capacity, we want to find the fastest delivery route. And one question is, how would we do such a thing? Well, first, we'd want to be able to estimate the travel time between all locations. So once we have that, then we can figure out a good way to order within a good way to order these travel time locations to minimize travel. And lastly, we want to return the amalgamation of all of these different travel times back to the user here. And we have 45 seconds to do so. So a common strategy is you might want to find a crude solution really early on and use methods to potentially further optimize that solution if you have more time. So this could be represented by a matrix where on one side you have all the intersections where you start, and on the other side you have all the intersections where you can end. And to estimate travel times, one option is to estimate by distance. So this is not considering the path. So you can imagine that it could be a good first order estimate if 2 points are closer together. If you were to take the Manhattan distance, for example, if 2 points are closer together, they should it should take less time to travel. But there could also be some corner cases, such as, let's say 2 points are physically close together on a map, but the path between them has to circle through or has to redirect the user to a highway, then it might not be the most accurate. So a more accurate solution is to actually get the path between all points. But you can imagine that this is accurate, sure, but it's slow. So roughly, here's like some pseudocode to get the travel time matrix. So it's the matrix that we saw in the previous slide, and this is roughly an algorithm that we've probably went over, and maybe a poll isn't even necessary since there's only one of you. You could even type it in the chat here. So things to consider here: we have k depot pickup drop-off locations, and we have n total intersections. And the other thing to note here is we have a doubly nested loop here. So you might want to consider how long do we spend in each of these loop iterations, given that it's a doubly nested loop, and given that we have k depot pickup drop-off, what's the complexity here? So
Naif, I'm launching the polling. Everybody gets to vote.
All right.
Plus, it shows you the options. So Andrew, you should vote too.
No need to be shy here.
Just take a shot at it.
Yeah. Oh, my phone froze. 1 second.
All right, so I'm going to end the polling soon. And we got one. Anybody who's left wants to vote, do it in the next few seconds. Just take a shot at it. Okay, I'm going to end polling.
Okay, so, all right, so we have 2 votes. Awesome. Okay, cool. And they're both close. So one is correct. So it's k squared n of log of n. So why this is the case? Well, it's mainly this doubly nested loop here, right? So each iteration of the loop, we have each iteration of the loop, goes k times. So hence it's k squared n log n.
So yeah, so just
And
A star is basically n log n in a graph with n intersections. It will go through, in general, most of the graph, so that's order n. It sorts everything that's in the wavefront, so that's log n. And then, as Dave said, there are two loops here. We're basically only finding a path from one source to one destination. So we have a doubly nested loop to find all possible source destination pairs. So that's k squared. So that actually can get kind of big. So I'll stop sharing that now.
yeah, and as Vaughn alluded, yeah, it can get kind of big, and especially on large test cases where we have 500 intersections, so that's 500 squared. So you can get into a bit of a hairy situation if you use this A star approach here. So if we were to look at another algorithm here, so it's very similar, but just note that instead of the doubly nested loop here, we have a single loop. So, and the parameters are the same, k, depot, pickup, drop-off locations, and instead of A star, we have multipath Dijkstra. So let's do another complexity poll here. What you think the complexity of this algorithm is.
Okay, just a reminder, multipath Dijkstra from one source, it finds the path to all of the destinations, so all k of them in one invocation. So the question is, what's the complexity of that algorithm? And then what's the complexity of this overall block of code with the loop? All right, so you've got another poll up.
All righty.
I'll give you another few seconds. So we have a new participant joining. See how fast you can get up to speed and see if you can participate in the poll.
So for the new participant here, we're asking how long a multipath Dijkstra can take for pathfinding. So this is the pathfinding algorithm that Professor Betts, or traveling Courier problem that Professor Betts went over in class. We have k depot pickup drop-off locations and total intersections. And roughly this algorithm has a single loop iteration that goes k times, and inside the loop we have a multipath Dijkstra. So given that we have the structure here, we're trying to just get a gander at what you think the complexity of this is. Ooh, maybe like 10 more seconds and let's...
Okay, we're in the last 10-second countdown, so take a shot at it. It's fun to click on these polls.
Alrighty, okay.
Okay.
Cool.
So I'm going to end the polling and share the results.
Okay, so yeah, most of you got it right. It is k of n log n. So one loop iteration of this takes n log n times, and we're going through this k times as opposed to k squared times when we were looking at the A star approach. But because in a single iteration with multipath Dijkstra, we can get the single with a single source to multiple destinations. We don't have to go, we don't need the second loop here that we needed for A star.
And these kind of questions are some of the favorite ones for, some complexity questions. How does this algorithm work? These are some of the ones the TAs really like to ask in the final presentation. So again, just to walk through this, multipath Dijkstra. In a graph with n intersections, you will in general explore them all. So that's your n. You're going to be sorting them in a wavefront. So that's your log n. And then the loop is over k starting points. So that's your kn log n. And as Dave said, we've gotten rid of one entire loop because this algorithm can find multiple destinations, so it's a lot faster for this kind of problem.
Awesome. Alrighty, so okay, so this is great. We've already seen that even without like in a single threaded approach, we can improve speed here. But we might ask, what if we want more speed? Well, there's parallel programming here. So there is still a lot we can do in the algorithm front to do as well as we can, But if that's still not good enough, we can look at parallel programming. So a lot of this Professor Betts went over, so I'm going to quickly skim over this. So this is just a picture of a multi-core processor. Here we have 4 different cores, and they can all communicate with each other through shared memory here. So that means that one core can write to a variable that another core can see, and through that, different cores can communicate. Also, cores can get their own bits and pieces of memory here if you're careful with how you distribute the memory. If you want to learn more, you can take computer architecture, which actually goes into how these multi-core processors are made. And you can also take operating systems. So typically, your operating system is responsible for scheduling bits of computation to these in different cores. So you could learn more in those courses here. All right, so typically, until you've done parallel programming, you've written applications that take a single thread here. So that gets put onto one of your 4 cores here, or in a 4-core machine, and it gets full access to the memory here. Now, because you have nothing else competing for memory, you don't have to worry about the nuances of sharing memory. So you can imagine that if you have multiple cores, all reading and writing to a bit of shared memory here, there could be a lot of nuances with that. When you're writing a single-threaded application, you don't have to worry about any of that. Now, when you're writing multi-threaded applications, that is something you need to worry about. You need to worry about the order in which different threads, or which are bits and pieces of computation running on different cores, are reading the same amount of memory here. Multiple variables could modify the same variable, and that could create problems in your program. And we're actually going to show that happening today. So stay tuned. So here's an example of simple parallelization. We have this loop where we're doing a large vector addition. So we have 3 vectors. We have a C vector, which stores the result, and 2 other vectors, A and B, that have numbers that we want to add. We add a pragma, OpenMP parallel 4. And what that does is it divides up the work here. So you can see that the large for loop has 100 iterations. It divides the 100 iterations into 4 groups of 25 iterations and forks it off to 4 different threads at the loop body here. And it can do that because if you look at the actual computation that's happening here, all iterations of the loop can happen independent to one another. They're all on independent I values. And then what happens after the for loop, they all serialize at the end, and we get the statement done. So this is a simple example of just adding a simple pragma at the beginning of your loop. You can actually spawn off your computation to 4 different threads. So I'm going to give a brief demo here. So I'm going to stop sharing the slides for a second, and we're going to get into an actual example, okay? So give me a quick second here. I'm going to reshare. Okay, cool. All right, so briefly gonna just go over the code again. So this is very similar to the code that I've shown in this previous slide. So the previous slide was simple vector addition. This is a bit more computation here. Why did I put more computation? Well, when we're parallelizing our code, we can get more of a speed up if there is more compute to divide amongst the threads. So instead of doing a simple addition, I've added some multiplication, divisions, a modulo operator to make it a bit more interesting here. The other thing to note here that we can change is we can also change the length of our vector here. So this is the amount of work that I'm giving to my threads. So if we remember in the last slide, there were 100 total iterations that we forked over 4 different threads. Ideally, you would want to give it as much work as possible here. So first thing, I'm just going to quickly comment out this code. We're going to get into this specific line later in the demo here. But for now, I have a vector length of 1,000. And I'm going to try to fork that across 4 different compute threads here. So clean and make. Okay, so, oh, sorry. The other thing to note here is I've also commented out the OpenMP parallel. So this is the serialized version here. So we're going to run this serially, and we're going to run a computation of this computation with multiplies, divides, modulo operators over a vector of a length 1,000, okay? So when we see that, we see about 3.6 times 10 to the negative 6 seconds. And maybe what I'm going to do is I'm going to, let's say, okay, we see that. Maybe I can even do better if I throw more cores at the problem here, right? So I already get a decent amount of time. If I throw more chords at the problem, this might help me divide the problem's the compute time up. And I have 4 threads, so maybe you'll divide it up by 4. So right now I've uncommented out the parallel operator. So this should parallelize my code. And let's try this out. And actually the opposite happened here, right? So it didn't get faster, it actually got slower. And this is because we're introducing parallelization into your program actually adds a bit of overhead. And in order to amortize that overhead, you need to give it more work. And this could be because our vector length isn't long enough, right? So what I'm going to do is I'm actually going to increase the amount of vector length so that there is more work to be split across the cores here. And sorry, I'm going to actually run this serially first. And let's see what happens. Okay, so serially we see about 0.003 seconds, whereas in parallel, we see a bit of a speed up, right? But this is maybe about like 1.5 times speed up, not nowhere near the 4 cores that we have, right? So what I'm going to do is I'm going to actually give it even more compute because it's still, we still might not be amortizing the full cost of parallelization here. So I'm going to increase the vector length. I'm going to serialize it again so we can see the effect of our speed up. Okay, so serially, this took about 0.336 seconds. And I'm going to introduce parallelization again. And we see this running at 0.99. So 0.33 to 0.099, sorry. And that's about 3.4, 3.5x speed up. So it's not exactly 4, and that's and the thing is, you will never get perfect speed up. So there's this is as close as you can get, probably because we do have quite a bit of computation in our loop. If you have even less computation, but let's say you're bounded by something like memory, then you might not even see close to a 4x speed up if you were to throw it at 4 different cores. The reason here is we still have that little bit of parallelization overhead that we're paying a cost for. So hence, that's why we're not seeing perfect 4x speed up. But you're going to see a lot less if your problem isn't compute bound, as in if there's not enough compute happening inside your parallel loop. So I'm going to go back to the slides here. Oh, wait, sorry, 1 second.
Jump into a couple of things. So I guess just to clarify the overhead, the primary overhead that you're hitting here, we're hitting here is creating a thread, creating a set of threads takes some time. So it takes a fraction of a second, but on something that doesn't take that long like this, that's still noticeable. So that's the key reason that as the work that you do gets bigger, you're getting better speed ups. Initially, the creating 3 more threads takes more time than the speed up you're getting by dividing up work, so it's not worthwhile. As the work gets bigger, you gain. You've talked about 4 threads because there are 4 cores, so you know there are 4 threads running because OpenMP will by default try to use as many threads as there are cores. But maybe it's good for you to, I think you're about to show, how did you figure that out? Like if you didn't know how many threads were being created, because there's nothing in here that says create 4 threads. You're just telling OpenMP, make this as parallel as you can.
Yep.
So maybe I'll hand it back to you. I can see you're about to show, how do you figure out how many threads are actually running?
Exactly. So here there's this line here that says OpenMP get num threads, and I actually commented that out because it actually adds a bit of time inside the loop. So I didn't want that to be part of the measured time that we were doing for our computation. But I'm going to put that back in just to see how many threads we have. And then I'm going to rebuild it here. And we have 4 threads. And that's because we're running on a 4-core processor with no multi-threading here. Sorry, with no hyper-threading. So we have OpenMP launches exactly 4 threads, 1 thread per core.
Yeah, so it'll be different on different machines. It automatically works it out for you based on how many CPUs are on your machine. And Naif, as you said, it slows it down quite a bit. So this went from basically 0.1 seconds to 0.35. So this actually slowed the program down by a factor of 3.5 times. So you wouldn't want to leave that thread counting in your loops when you're really finished with your code.
Mm-hmm. So I'm going to go back to the slides here. If I'm going to stop the share here, unless if anyone has questions specifically about this. Okay. All right, so this is just a summary of what we've seen in the demo here. So again, when our vector length is very small at around 1,000, we actually see the serial significantly faster than the parallel. Again, we're paying a price to parallelize, but we're not amortizing it enough over enough work here. So once you start to increase it, we actually do see the parallel catching up to serial, but it still hasn't crossed the point where we've amortized the parallelization cost, the cost of making these threads. At some point, we do see that we can amortize that overhead. So at this point, we start to see a speed up, but we can still throw more cores at the problem, or more work at the core, sorry. And at some point here, we've fully amortize or amortize as much as we can here, but speed up is still not perfectly for, because again, there is still that overhead that we're paying for. So at this point, I'm gonna hand it off to Professor Betts here, and he's going to talk about fast pathfinding and even give a neat demo. I think he might be looking for or setting up the demo right as we speak. So.
Okay, so can you see that, Dave?
Yeah, I can see that.
Okay, so these are results from running a problem with actually 24 deliveries and pickups. The 20 is a little bit out of date. And it just shows what speed up we can get by changing the algorithm and by going parallel. So if we run our A* algorithm that goes from one source to one destination, and we use 2 loops, over k. So we have that k squared n log n algorithm that we showed a few slides ago. That took 32 seconds in our reference implementation. So we define that to be kind of 1x speedup. If we change the algorithm to multi-target Dijkstra, now we only have to have one for loop, as Nave showed earlier. Time drops a lot, down to less than 6 seconds. So we got a 5.5x speedup. And that speedup would grow as we went to larger problem sizes. So that's great. What if we parallelize it? So I'm going to show you the results here, then I'll show you a bit of the code in a minute. If we take the iterative A star algorithm, and so we have 2 for loops, we can basically just say run one of those 4 loops using an OMP parallel for. So we're running a bunch of them at the same time. The time drops to 9 seconds, so that's a 3.5x speed up, so pretty good. 4 cores, we got almost a 4x speed up. And the best solution is actually improve both the algorithm and parallelize. So if we take that multi-target Dijkstra, which has a for loop in it, and we make that parallel, then the time drops to 1.8 seconds for an overall speed up of more than 17 times from where we started. I guess the takeaways from here is that algorithm improvements were actually a bigger gain. Multi-target Dijkstra got a 5.5x speed up. Parallelization got about a 3.5x speed up. So they're both significant, but algorithm improvements were more significant. And that's generally true. Across a wide range of problems, you should try to improve your algorithm first. You can usually get bigger gains by doing that. And the gains we got from the algorithm would be even larger on larger problems because we've actually changed the complexity of our approach. So before you go to parallelism, make sure you've got a good algorithm. Once you hit the wall on that algorithm, though, parallelization is getting us a good additional gain. All right, so let me go and switch the screen share to show you my screen. Okay, I'm going to stop your screen sharing, Nath, and let me know if you can see my screen in a moment.
Okay, sure.
Okay, can you see that?
Yeah, I can see that.
Okay, so this is a piece of our reference solution that the teaching team and I have created for the course. And it's big, so I'm not going to walk through all of this, but you don't need to understand it all. What I'm showing you is the high-level code, the high-level control code that performs the path finding to load up that matrix of delays between all of our pickups and drop-offs before we start optimizing their delivery order in Milestone 4. Okay, so we've got the multi-destination Dijkstra, find multiple paths from intersection MT. So from a certain source intersection I to all of the destination intersections that we're interested in, we're gonna invoke a multi-target Dijkstra algorithm. And we have to do that in a loop. So we loop over all of these source intersections, basically all of our delivery locations. So that's basically the same as the pseudocode that you just saw. And this pragma, OMP parallel 4, means we can run that in parallel. And I'm going to start by not running it in parallel. So let me comment that out. So now this is serial code. It's going to be run in one thread, the conventional way. I've got the unit tests. I've basically copied over into my unit test source directory. One of the tests is Toronto Easy, which is got 24 pickups and deliveries. So K equals 24 in the problem I'm about to show you. Okay, so I'm going to build unit test release. Whenever we want to do timing measurements, we should always be using the release code. So we've got all our optimizations. Okay, so I'm going to build that. And then I'm going to run it. I'm not going to run it through the debugger. I just want to run it and see what happens. Okay, so it's built. And now I'm running it. Okay, so you see some output coming out basically from our load map. So we're loading things up, we're organizing it in data structures. Load map's done. It took a little under 8 seconds. And the next thing we're doing is building that matrix of travel times, and it's done. And it took 6.7 seconds. And now you can see we're starting to optimize the delivery order. And we'll actually do that until we run out of time, which is almost 45 seconds. So I don't actually want to wait for this to finish. So I'm just going to stop that. So the key thing is that it took 6.7 seconds. All right, that's how long our pathfinding currently took. Now let me turn on parallelism. Okay, so I just put on brought back my parallel 4 pragma. Okay, I rebuild my unit test release. And then I'm going to run this, and we'll see how much faster it is. Okay, so I'm running this new version of the code. The map's loading, so it's been loaded, and now we're doing pathfinding, and that took 2.9 seconds. And now we're into optimizing delivery order, and again, we'll do that till we run out of time. So we got a pretty good speed up there, 2.9 seconds. We didn't get quite 3 in this case. Sometimes CPU time measurements can vary a little, so I'm just gonna run this again to see if I get the same answer again. They can vary based on machine load and what's in memory and so on. So let me run it one more time to get a little more faith in the numbers. This time it took 2.4 seconds. So it was a little faster. It's probably because more data was in memory. So that's closer to a factor of 3, but not quite 3x. So we got a pretty significant speed up. You know, what can we do with this reduction in time? Well, for a big problem, pathfinding actually turns out to take up most of our 45 seconds. That 3x speed up means that it won't take up, instead of taking maybe 40 seconds for a big problem, it'll take more like 15 seconds, leaves us a lot more time to optimize. So it's worthwhile. Now let me show you some gotchas. So far this all looks really easy. I have a for loop, I said make it parallel, and I got a speed up. So that sounds like I should just go over my whole program, putting parallel for in front of all my for loops, and life is gonna be easy. Let me show you that life is not always so easy though. Parallelization is tricky. What I'm showing you now is a piece of that multi-target Dijkstra, okay? So the multi-target Dijkstra algorithm calls this routine, which actually does the real work. I'm not gonna show you the whole routine, it's relatively long, but basically inside of it, we need a priority queue. We need a couple of key variables, a priority queue, and we also need this vector that stores the information about nodes that we've reached. So the reaching edge, the best time to every node. So this is a vector over all the node IDs that stores some information that our Pathfinder needs. So for every single node, what's the best time we found to it? What was the street segment ID or reaching edge that we used to get to it? These are both local variables right now, and I showed you that it works fine when I parallelize things. But let me go show you that it doesn't always work fine. So these defines, I can actually break the implementation by just undefining. Okay, so basically when I took that comment out, I've now defined something called bad parallel global 2. All right, so now the C++ preprocessor is going to compile this code. It basically says if this preprocessor variable bad parallel global 2 is defined, then compile the code underneath. And the code underneath just declares priority queue to be a global variable. Okay, so the name of my priority queue was traversal queue, and I've made it a global variable. And let me go back to where I was before. And you see this is inside my Dijkstra's multi-destination Dijkstra algorithm. And I'm no longer declaring the local variable. Okay, so basically I've just quickly flipped the code from a local variable priority queue, which is really better code style. You should try to keep your variables as local as possible, to a global variable priority queue. And now I'm gonna rebuild. So yeah, so this is, I'm not showing you good code style here. I'm showing you something that's inferior code style, but is commonly done. You might have global variables or variables that are defined outside the for loop that you are parallelizing that you pass in. And those are a problem for parallelization. So let's see, does anybody want to weigh in on whether they think this is going to work or not? Let me bring up the chat quickly and see what I can see here. Let's see. I don't know if I can find my chat very quickly. So all right.
I can see it. No one has weighed in yet.
Andrew, what do you think? Is it going to work? I'm going to call on Andrew.
It will compile.
It will compile. Okay, so let's see. I did just compile it, so you're right. Now, is it going to work if I run it? What do you think? Not sure? I'm taking that.
Let me see.
Okay, so let's just go ahead and run it. Okay, so I'm running it now, and let's see what happens. Okay, so the map is loading. Doesn't look good. Okay, so the map is loading. That was all fine. Load map worked. And then I got basically memory corruption. So it says you tried to free something twice, which is not allowed. Where did that come from? This is not incredibly useful. It basically says somebody tried to free memory twice, and that's not allowed. Okay, so this is a hard crash. Now, when you're debugging parallel programs, they are fundamentally harder to debug than serial programs because you have multiple threads collaborating, and they can stomp on each other's data. They can do very subtle things that break your program. So the first thing you do when a parallel program fails is you turn off parallelism and see if it fixes it, okay? So I'm gonna basically turn off parallelism, comment out this pragma OpenMP parallel 4. I'm gonna rebuild. And I'm going to run it again. I'm going to see if this works with the serial code. So what do you think? Does anybody want to weigh in on the chat? Do you think this is going to work now? So I've got a global priority queue. Did not work when I was parallel. Is it going to work now that I'm back to serial? So Andrew, I'm going to call on you again. What do you think? You thought you were going to have
yeah.
parallel. Not so easy.
I think it will work.
Okay, so you think it'll work. If anybody else on the line wants to weigh in, I'll be nice and not call on you. I'll only pick on Andrew. So let's see. So Andrew thinks it's going to work. Okay, so I'm running this version of the code. Okay, so we're loading our map again. Load map is done. And now we'll be doing that pathfinding to load up that matrix of travel times between all our destinations. And it worked. And it took 6.4 seconds. So it worked about as well as it did with a local variable. Serial code doesn't care, works fine. So yeah, this is the first step in debugging this. I'm gonna stop this because I don't actually care what happens after this. I'm gonna now, okay, so we've learned something interesting. It works when it is serial, it doesn't work when it's parallel. So we've got a parallel problem. Parallel problems are usually about accessing shared memory. That's normally what causes a program to fail when it's run in parallel, but work when it's run serially. Okay, so I'm gonna make this parallel again. I just uncommented my parallel pragma. I now wanna run this in the debugger. So I'm gonna change my build type to unit test debug, and I'm gonna do a clean and build. So this is gonna take a few seconds. You're gonna see some warnings because what I just did, basically changing from a local variable to a global variable with the same name, it's a little bit messy, and the compiler says it's a bit messy. You got some variables with the same name, doesn't like it. It's fine, you know, so you shouldn't submit code with warnings, but I did this on purpose to demonstrate something. It's not very clean code. All right, so this is continuing to build, and when it is done building, I'm just gonna fire up the debugger. Okay, so it's done building. I'm not even gonna set a breakpoint because I know that this actually crashes. I just wanna run the debugger and see where does it crash. Okay, so it's gonna run a little slower because all our optimizations are turned off, but we're loading our map. Took 9 seconds now instead of 7, so it did slow down some. And now we know we're into pathfinding. Pathfinding was taking about 6.5, 7 seconds. It's gonna take a bit more now that it's debug. So, you know, this might take 15 or 20 seconds now that I'm in the debug build. But this has been going on for a little while. So I'm starting to get a little nervous. You know, is this actually going to complete? So let's give it another 20 seconds or so, 30 seconds. But at that point, given that this finished in finished about 7 seconds in release build, you know, really shouldn't take longer than, you know, maybe 4 times that. So 30 seconds should be fine. And we've already given it probably 45 seconds. Now we're getting close to a minute. It shouldn't be this slow. All right, so I'm getting worried. Actually, it's also parallel. When I did the parallel version, it actually only took about 2 seconds. So this is way too long. Shouldn't be taking this long even when I turned off release build. So I'm gonna pause. I can go up here and I can hit this pause button to see where am I. Okay, and that's paused my program. Now, you've probably never used this window before because there's been no reason, but if you go to Window, Debugging, you can open a window called Threads. And I've already done that. Okay, so Threads is open down here. I'm gonna click on Threads. And you can see that I actually have 4 threads because I'm inside that parallel 4. 4 threads have been created. The one that's bolded is the one that the debugger is currently telling me about. Okay, so let's click on that. That just makes sure that it's that thread. And I can look at the call stack to see where is it. Okay, so where am I? I'm inside an allocator for a vector. So it's trying to allocate a vector. And how did I get there? It basically, let's see, basically inside my multi-threaded Dijkstra. So I am in the path search. And I was trying to ask if the priority queue, I just asked if the priority queue is empty or not. And that went off and tried to do some allocation. So I'm not quite sure why that happened, but that's where that thread is. Let's look at the next thread. So I just clicked on the second thread. Let's look at its call stack. Okay, so where is it? So again, I'm in the multi-threaded Dijkstra, and I'm actually trying to, like the top of the call stack is the very last function I'm in, but that's a function that I didn't write. This is again deep inside some iterator function for a vector. So I see what called that. It's again some standard library function, so I didn't write that. What called that? It's a priority queue function inside the standard library, so I didn't write that. So now I'm into code that I actually did write, which was I was trying to pop out the lowest cost entry from the wavefront. So I was trying to take something out of my priority queue. So now let's go look at where the next thread is. So the next thread, third one, I go look at its call. So I double click on it, it's active. I look at its call stack. Now the last function it's in is again way down in inside of the vector standard library. If I step back to where did that come from, still in the vector standard library, still in vector standard library. I'm inside the priority queue, which uses a vector as part of it. Now I'm finally back into my code, and my code is checking, is the queue empty or not, the priority queue. So it's asking a question of the queue. Okay, so I'm getting a little bit of an idea here. I've got basically, so far, all 3 threads, they seem to be hung. They're just sitting there. They're not coming back because I waited a long time and the program never finished. And so far, all 3 of them are in operations on the priority queue. 2 of them are asking, are you empty? And 1 is trying to remove something from the priority queue. So let's go look at the 4th one. Okay, 4th one, look at the call stack. And again, the last thing is deep in the standard library. So I want to see what was I calling? I was calling top. Top is get me the smallest entry from the priority queue. So I don't know exactly what's happened here, but what I can tell is that all 4 threads are trying to access the priority queue at the same time. 2 are asking if you're empty. 1 is trying to remove something from the queue, and 1 is trying to say what is on top of the queue, or what's the smallest entry. So what has probably happened here is because I have 1 priority queue, this is chaos. I have 4 path searches happening at the same time, and all 4 of them are using the same priority queue. So they're shoving in different entries into the wavefront. They're taking entries out of the wavefront. They're all corrupting each other's data. So this is not going to work. And in fact, they're corrupting each other's data so much that they're hanging the priority queue. The priority queue has gotten into a strange state where it's actually not returning from its functions. And it was never written to have 4 different threads simultaneously trying to put in and take things out of it. So this is an unsafe use of a priority queue, and it's actually hanging it. And there is no way this could ever work anyway, because you can imagine we need 4 separate priority queues. We can't use one with all the data interleaved. And in fact, we get an even worse behavior of it. It's actually hanging. So I'm going to stop this, right? Because it is hung. I'm going to just run it again. Let's see what happens if I run this debugger again on this program. And let's see if the same thing happens or not. Because when I ran the release build, it actually had a double free and it crashed. When I ran debug build, it hung. Let's see if I run it again, if I get exactly the same behavior. Does it hang or does something else happen? Okay, so I'll give it a little while. It looks like in this case, it's going to hang again. One of the other tricky things that happens in debugging race conditions, this is called a race condition. I have more than 1 thread trying to access shared data, and at least one of them is trying to write to it. It's okay for multiple threads to access shared data, like a global data structure, if they're all reading, because that's safe. Nobody's changing anything. So if you had a graph that stores what intersections are adjacent to other intersections, and you only read it in your parallel for it, that's actually okay. That can stay global. But this priority queue, we're not just reading, we're also writing it. And that's chaos because we don't know what's going to happen. Now, it looks like we're going to basically hang again. If I go look at the threads, let's go see where they are. This one, let's look at, I picked the fourth one, look at where it is in its call stack. It's actually back talking to the priority queue again. So it looks like this typically is causing a hang. But one of the tricky things about debugging these race conditions is every time you run the program, your threads can execute in a slightly different order, and you can actually get different errors. They're all caused by the same thing, undisciplined access to shared state, but it can be tricky to figure out. The program is non-deterministic. It actually can produce now a different error every time you run it. So if you see that kind of behavior, that's common with race conditions and undisciplined access to shared data in parallel programs. I can produce the same problem by, I showed you how to do it with making one variable global, the priority queue. If I take this all nodes, which is our data structure for storing the reaching edge and the best time used to find every node, and I make it global, it will also cause the program to fail, and it'll fail in a different way. So I go back here, let's just finish off by fixing this. So let's go back and fix it again to show that this does work if I get rid of this. All right, so I broke this by making what was a local variable global. I'm going to turn off this define, and now this turns gray to say this code is not active, it's not being compiled. I'm back to my local variable. I'm going to stop debugging. I'm going to compile the, I'll just leave it in debug. I'm going to compile this, and I'm going to run it, and now it should work fine again. Okay, so let's run that. Okay, so my load map is done. Hopefully my pathfinding finishes shortly, and it did. It took 6.5 seconds. That's slower than it was before because of the fact that I'm running a debug build right now. So it is parallel, but it's debug. So I've got the benefits of parallelization, but I don't have optimization. It's not as fast, but clearly it now works again. So my problem was indeed that global variable. All right, so let me go back and just wrap this up with the final slides. Or maybe, Dave, I will get you to share the slides again. Does that sound good?
Yep, I can do that.
Okay, so this code just shows basically a pseudocode or skeleton code of what I just showed you. The problem that I was having is I had a shared global, this priority queue, and multiple, once I went to a parallel implementation of my pathfinding, it was chaos. I had multiple threads all trying to write to this shared priority queue, and that caused a variety of different bugs. So in order to make this loop parallel, it's not enough to just say, tell OpenMP to make it parallel. I also have to make sure that I have privatized any shared state that I'm going to write to. So in this case, we're going to change the priority queue. We need to have a privatized version of it. We can't have it shared in one global variable. Again, if it was stuff that we were only going to read across all threads, so that might be the adjacency information of the graph, that would actually be okay to leave in one global copy, but not anything that we're going to change. Okay, so debugging parallel programs. It's tricky. First step is disable parallelism and see if the problem disappears. If it does, then you've localized the problem to it's something with your parallel structure. The most common thing is it's a race condition, meaning multiple threads writing and reading from a shared variable. At least one of them has to be writing for this to be a problem. Once you suspect it's a parallel race condition using this first technique, you can run in the debugger. You use that window debugging threads window. So that's how the menus you use to turn it on. And then you can see the different threads. You can click on them. You can examine their call stack to see where are they all. If they're all accessing a shared variable or several of them are accessing a shared variable at the crash point, then it's likely a race condition. So in our case, we saw that they were all working with the priority queue, which is a strong hint that that's our problem. How do you fix these conditions? So the best way to do it is to privatize a variable. So you take a variable that's declared outside of the part you're parallelizing, so outside of that for loop or the functions that it calls, and you move it inside. Make it a local variable within the parallel for, within the functions it calls, and now every thread gets its own copy and it's safe again. In a few cases, you can't do that. Let's say we're using cout, the standard output. We can't make a different copy of cout for every thread. What you do for things like that, where it's important that only one thread access it at a time, is you use OMP critical to say only one thread can access it at a time. This is not as good a solution. You don't do it as your first resort because it can hurt performance. And in many cases, it's not good enough. For our priority queues, we really need one per thread because they each need to have their own state. Even if you put OMP critical around one shared priority queue, it's not going to work because they're still going to be writing over top of each other's data and causing chaos. Limits to parallelization. So Nave showed you one. You need to have enough work that it's worth the overhead of creating threads. Another is called Amdahl's law. So let's say we have n cores, in our case it's 4, and we have a program that is partly parallel code, say pathfinding, and partly serial code, say our code to optimize the delivery order. Only the parallel part of the program is going to get faster as you add processors, so that puts a limit on your maximum speed up. And this graph shows it. As you go on the x-axis, you get more and more processors. On the y-axis is your speed up. If your program is mostly parallel, so 95% of your time is spent in code that can be run on multiple threads, then you could get up to a 20x speed up if you have enough processors. But if your program is only half the code could be sped up with parallelization and half fundamentally can't be, it's just fundamentally serial, then your maximum speed up is just 2, no matter how many processes you throw at it. So that's an important thing to think about before you put a lot of effort into parallelizing something. How fast can you make this program? If you're parallelizing a small part of a mostly serial program, it's probably not worthwhile. If you want really big speed ups, you need to have most of the program being parallel or a very high fraction. Takeaways: improve your algorithm first. We kind of hit on this a couple times, usually bigger rewards. Adding OpenMP pragmas is a pretty fast and simple way to add parallelism. There are other ways, but this is probably the simplest. Avoid modifying shared state because that minimizes bugs. And you want to privatize variables so that every thread has a copy. Parallelize large chunks of work to minimize the overhead of creating these threads. And it fundamentally is hard. Even if you follow all of these rules, parallelizing things is not that easy. Some things are easier than others. You know, the parts of your program we're recommending you consider parallelizing, like pathfinding, are what's called embarrassingly parallel. It means there are no dependencies, no communication between the threads. Those are the easiest things to parallelize. As you get into algorithms where there is communication between the threads, they get harder to parallelize. And let's see, think about. Okay, so M4 suggestions. So we always emphasize agile development. Get something simple working first. So you may use a simple travel time heuristic like geometric distance rather than exact path delays, a simple ordering heuristic. So maybe one of the algorithms we talked about in the early lectures that are greedy solutions, and you get a legal solution going. And then you can try various things. Get better cost estimates by pre-computing exact paths. You can use perturbation operators to try to get better delivery orders, and you can try to parallelize to stretch your 45-second CPU time budget. But always focus on getting a working solution quickly and then improving rather than doing the most complicated things first, like parallelization. So that's everything for today. Let's see if there are any questions on the chat. If there are no questions, then we are done for today. So I'll give you a few seconds to think about it. And if nothing comes up, then I'm going to stop the recording. Okay, thanks everybody, and good luck with Milestone 4 and with all of your exams.
Yeah.
See you later.